hiya, 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 hiya. Hi everybody. Today I'm going to solve the two-stage rocket problem. I've been helping a couple high school students last week, and this problem has come up a few times, so I figured I'd make a little video explaining how to solve this problem. The level of this problem is high school physics, honors, or AP physics. And the question is, we have a toy rocket that accelerates for a certain amount of time. In this case, let's just take 10 seconds, and the acceleration will be 20 meters per second squared. So I have two questions. First, find the maximum height of the rocket, and secondly, find the total time that the rocket's in the air. Okay? So if I just illustrate that on the diagram, so we have this first part of the trajectory. This is the first 10 seconds here. Okay? And for 10 seconds, we are accelerating at a rate of 20 meters per second squared. So let me just write that like that. 20 meters per second squared. Okay. And the time for this first segment will be 10 seconds. Okay. The second part, the acceleration, is also known actually. It's not explicitly said in the problem statement. However, once the rocket turns off, the acceleration is simply going to be acceleration due to gravity, which is minus 9.8 meters per second squared. For this problem, let's just simplify that and just write it as 10 meters per second squared. It'll make the numbers work out a little bit easier. Okay, so we have 20 meters per second squared for the first 10 seconds, and for the remainder of the trajectory, we're going to have minus 10 meters per second squared. So we want to find, the first question is simply the maximum height. So they're looking for how high it will go here. Let's call this h. And the total time. So that's going to be the total time to get to this maximum height. And then we're going to have to add the time it takes to fall back down and land back on the ground. Okay, so before starting to solve this problem, let's just review some of the basic kinematics, kinematic equations for 1D motion. The one thing that you have to remember for this problem is the acceleration is not constant, right? It goes from 20 meters per second squared, and then once the rocket turns off, it switches off, or the acceleration becomes minus 9.8 meters per second squared. Okay, so you can't just use one equation to describe the whole motion. All the equations you've seen in kinematics in your physics class, those equations only apply for constant acceleration. But that means we can apply those equations for the first part, and then we can also apply those equations for constant acceleration for this whole green trajectory here, for the part where the acceleration is minus 10 meters per second squared. So let's just review those 1D kinematic equations. Reviewing 1D kinematics. So again, the one requirement here for analyzing the motion here will be that the acceleration must be constant. Okay. If we have constant acceleration, I can write down a series of expressions that allow me to describe the motion. So what I want to do is I want to be able to describe the acceleration. I want to be able to describe the velocity. I want those expressions to involve time. I may want to describe the displacement. And I may also want to solve for what the initial velocity was. So we kind of have 5 different variables. That we need to describe the motion. Now when I write the displacement as a change in y, what I'm really talking about is the displacement minus, or the position minus some initial position. Okay. So I have 5 variables. I can actually write down 5 different equations for 1D kinematics that I can use to analyze the motion. Okay. The first one will simply say that the displacement is equal to the average velocity, which I can write as this, times the time. The second equation for my big five tells me that the velocity at any time is simply equal to the initial velocity plus acceleration times time. The third one I'll write as the displacement equals the initial velocity times time plus 1/2 at squared. I'll write a fourth one which also describes the displacement, and I'll write the displacement not in terms of the initial velocity but in terms of the velocity at any other time. And if you do that, you end up getting an equation that looks similar to number 3, except the sign is reversed here for this acceleration term. Okay, and the last equation I write tells me that the velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied times the displacement. Okay, so we had 5 variables. We have 5 equations. Okay. In each one of those equations, there's a quantity that's missing. Okay. So let me just highlight that for a second. So in the first equation, there's no acceleration. In the second equation, there's no displacement. In the third equation, there's no velocity. Fourth equation, there's no initial velocity term. And in the last equation, there's no time. Okay? So when I'm reading a problem and they don't mention time, they don't talk about the time, I know right away that I'm probably going to use big 5, number 5. Okay? This equation doesn't have time. It only includes velocity, initial velocity, acceleration, and displacement. Anyway, there's 5 equations. All of these can be derived, and they're all probably done in your textbook, but if you just want to memorize them, it's kind of nice to have all of these at your disposal. You just pull them out whenever you need them and try to solve the problem. So we're going to use a lot of these equations for the next, to solve the first problem, our 2-stage rocket. However, we have to remember for the 2-stage rocket that I can only use this equation when the acceleration is constant. So I can use these equations for the first part of that trajectory, and then I can use a whole other set of equations for the second part of the trajectory. But in each part I have a different acceleration term, so I need a different set of equations. Okay, so let me go ahead and see how I would solve the 2-stage rocket problem using these equations. Okay, so let me go back to my 2-stage rocket problem. We had that the first part, the rocket was accelerating at 20 meters per second squared, then the rocket turned off. And for the second part, we simply have that the rocket is accelerating at the acceleration due to gravity, and we know that's the acceleration is in the opposite direction, so it has a negative sign, and we're just going to assume it's negative 10 rather than minus 9.8 meters per second squared. Okay, the first question I had was, what's the total height? Okay, and I'm going to call that the total height h. That's what we're trying to find. Now, again, since the acceleration is changing, I can only use my kinematic equations in each of these sections. Okay. So for the first part, I can find the height, okay, or the displacement. Let's just call that delta y. For the second part, I could find a different delta y. Let's call that one green delta y, or delta y. Let's give it a subscript 2 here, just to differentiate it from the first one. Okay, and let's call this number 1. So the total height will simply be delta y1 plus delta y2. Okay. So let me write that. The total height, what we're trying to find will be the displacement for the first part plus the displacement for the second part. Okay, so we know for the first part we have an acceleration of 20 meters per second. We also know that the time that was given in the problem statement. That was 10 seconds. Okay. Now we're looking for displacement. That's delta y. And I called it delta y1 for this part. Again, there's no mention of final velocity here. So that automatically tells me that I should use big 5 number 3 from the previous page. And that equation was simply the initial velocity times time plus 1/2 at squared. So the rocket was launched from rest, so that first term vanishes. And the second term is simply 1/2, be 20 for this case. And the time was 10 seconds. Don't forget to square that. Okay, I can factor out that. I'm left with 10 squared, which is 100, multiplied by 10, which is 1,000. Okay, 1,000 meters. Okay, so that's the first part here. For the second part now, well, again, do I know the time? Let me just write down the variables. Do I know the initial velocity for part 2? And I'm really looking for the displacement, delta y2. Let me just write down the expression here and see what we have. So it's the initial velocity times time plus our 1/2 at squared. So in order to find the displacement, I need a few things. I need to know the initial velocity, and I need to know the time. So what would be the initial velocity here at this position? Well, it turns out that the initial velocity for this second part of the trajectory ends up being the final velocity for the first part. Okay? So once I'm at t equals to 10 seconds and I've been accelerating for 20, I've been accelerating at a rate of 20 meters per second squared, I'm moving pretty fast at this point. But then the engine shuts off. Okay, so the final velocity at the end of segment 1 becomes the initial velocity for segment 2. Okay, so I actually have to go back here and calculate what was this final velocity here at the end of this 10 seconds. And for that I can use big 5 number 2. It's the initial velocity plus acceleration times time. Okay, the initial velocity again for the first part was 0. For the second part now, we're left with 20 meters per second multiplied by 10 seconds. We get a final velocity after 10 seconds of 200 meters per second. Okay, so that's the key to this problem here is this here becomes, I drew that line a little too long here, this final velocity becomes the initial velocity for this problem. So let's erase this and just write down that variable since we know the value. So we're doing pretty good. We can almost find the displacement y2. All we're missing actually is to know the time. If I knew how much time it takes to go from here to here, I'd be able to find the total displacement. Okay. But now we have to use what we learned in our class, and we should know something about the top here, right? At the top, you should know that the final velocity equals to 0. Okay. And we can use that fact to find how much time it took to go from this point all the way to the top. Okay. So, at the top, v equals to 0 for this part. Okay. Now, if you use equation number 2, which is v equals v initial plus acceleration times time, I substitute 0 here, and I'm left with v0 plus at. Okay? The only unknown here is the time, which equals to minus v0 divided by the acceleration. For this problem, we know everything here. Right? We know the initial velocity was 200. And I know the acceleration is minus 10. Minus signs cancel out. We are left with the time is 20 seconds. Okay, great. So now we can substitute the 20 seconds in our displacement equation and find what the total displacement is for this second part of the trajectory. Okay, so let me just erase this and let's do that algebra. Okay, so the y2 displacement equals to our initial velocity, which was 200, multiplied times the time, which is 20 seconds, plus 1/2. The acceleration is minus 10, and our time was 20 seconds. And you can't forget to square that term. That's the total displacement for the second part. So multiply this through, what do you get? You get 4,000 for this first part, plus, take the square of 20 is 400. 400 times minus 10 comes minus 4,000, and I divide it by 2. See, this whole term becomes minus 2,000. Which means that the total displacement for that second part will be 2,000 meters. Okay. So the first question that we had in that previous part was, what was the height? Well, this is really what they were asking for. I have everything I need now to calculate how high this rocket went. In the first part, I calculated we had 1,000 meters. In the second part, I had 2,000 meters. So the total height will be 3,000 meters. Okay, and there you have it. That's the total height for that rocket, combining parts 1 and part 2. Okay, great. So the second part of the question was, what's the total time for the rocket to go all the way up and then to come back down to the ground? So actually, in this part of the problem, we already know how much time it took to go all the way up. For part number 1, that was given in the problem statement. We had 10 seconds initially. For the second part, we calculated it took 20 seconds for the rocket to slow down and to reach the top. So basically it took 30 seconds to go all the way up to the top. So all we have to do now is calculate how much time it takes to go back down. And we know the acceleration during this part of the trajectory. Therefore, it should be pretty straightforward. Okay, so let's go to the next page and calculate the total time. Okay, we're just about done the problem now. We simply have to find the total flight time. However, we know that the first part took us 10 seconds. We found that the second part on the way up took us 20 seconds. So now I simply want to find how much time it takes to go down. So the total flight time will be 10 to go up, plus 20 for that second part, plus the time to go down. Okay. And I also know that the height is 3,000 meters. I also know that the acceleration as it's going down is simply going to be minus 10 meters per second squared. I also know the initial velocity for this part of the trajectory. The initial velocity is 0 because I'm starting from the top, and at the top it's 0. Okay, so I know the displacement, I know the acceleration, I know the initial velocity. I'm looking for time. You can use Big 5 number 3. Simply says that the displacement is v0 times t plus 1/2 at squared. Okay. Our displacement now. Okay, so the displacement is simply going to be y minus y0. It's going to be equal to v0 times t plus 1/2 at squared again. Okay, we can simplify this a little bit. Since the initial velocity is 0, that term is can be thrown out. What about the initial position? Well, I can take the initial position as being 0. I'll just set the 0 up here. And I know that the final position is going to be 3,000 meters below. Okay. So let's set the initial position to be 0 right here. Okay. And I know I'm going to be 3,000 meters below. Okay. So the way you write this expression then would be 3,000 below, and everything below is simply a negative number. Right? Things pointing down are negative. That's why I have negative 10 meters per second squared for the acceleration. So I have minus 3,000 for my total displacement minus 0 is equal to 1/2 minus 10 times t squared. Okay, so the total time for this object to drop all the way down is simply going to be, simplify that expression, you get 2 times 3,000